How's it going, everybody? My name is Noah, and welcome to my AP STEM Corner. I've taken a total of 12 AP exams, so I've taken 17 by the end of this year, received all fours and fives, and have done particularly well on my STEM-related tests. Throughout my experiences tutoring these higher level classes, I've seen that students sometimes understand the material better whenever they hear it from a fellow student because it just offers like a more inexperienced point of view almost that can sometimes provide like simpler explanations, stuff like that. So I'm just starting these type of series to help as many students as possible kind of understand the materials in their classes. So let's get going. I will share my screen real quick. This particular series will be about AP Physics 1, and what I really want to hammer home is kind of just how important these FRQs are going to be. Because really, if you just kind of study the procedures for them and how to do them, if you get like two more points than maybe you would have on each one, you could still get a 50 on the MCQ, get a 4 on the final exam. If you got like 28 right on the MCQ, which is less than a 75, get a 5. You could get down to, you get like 4 right on the MCQ. If you just really work on these FRQs, then you can still get at least like a passing grade, and it just makes getting those higher scores so much easier. And why I really focus on FRQs instead of MCQs is that they're a lot easier to study for. Most of the time, you're kind of doing the same things regardless of like the material. So if you just like learn the processes and like kind of what exactly they want you to do with each verb, it's a little easier to understand and kind of like repeat it, get those questions right. So let's get started. This is FRQ1 on version J of the 2025 AP Physics 1 exam. It states a student has cart mass MC and block of mass has a car okay, I'm gonna restart that. A student has a cart of mass MC and a block of mass one fifth MC as shown in figure 1. At time t equals 0, the cart is moving to the right across the horizontal surface with the constant speed VC, and the student releases the block from rest. Students holding the block, cart's moving to the right VC at the speed VC. There's the cart. At time t equals 1, the block collides with and sticks to the top of the cart. The block does not slide on the cart. Block falls in the cart and stays there. They're still moving to the right. Time t equals 2, the block cart system continues to move to the right with the constant speed VF. So that's just kind of going with T1, but it's just showing they're moving at that speed. All right. I'm just gonna take some time to maybe to kind of label what exactly is going on in these diagrams. Let's see. I'm actually gonna make it an arrow. We have just VF and then VC. And those masses are going to stay constant. The masses of the block and the cart are going to stay constant. So since they're already labeled, you don't really have to label anything else. I just kind of like to do this so that I can go back and check and I know what's going on without having to read through everything. So on the axis shown, so part A says on the axis shown in figure 2, sketch a graph of the magnitude px of the x component of the momentum of the block cart system as a function of time from t equals 0 until t equals greater than 2. So our verb is sketch, magnitude of px, and momentum. So we're talking about momentum of the block cart system. One of the main rules with momentum that you should probably keep in the back of your mind with any of these is that P initial is going to equal P final. But that has a little bit of a caveat. It has to be if no external forces. So let's see. In this situation, is P initial going to equal P final? The block cart system, are there any external forces? Some students might say that this block falling is going to be an external force, but let's think about it. Moving right across a horizontal surface. Whenever this block is dropped, it's going straight down. All of its motion is going on the vertical axis. None is going horizontally. So, yeah, in the direction of motion, no external forces are happening. P initial is going to equal P final. If P initial equals P final, that means momentum's going to stay constant the whole time. So really, you just got to draw a horizontal line there. All right. I'm going to erase this, but kind of keep what we have on the prompt and then up top because that might be useful in later questions. All right, part two says derive an expression for the speed VF of the block cart system after time t equals 2 in terms of MC, VC, and physical constants. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. So our verb's going to be derive. The AP Physics 1 exam loves this verb. Because it is based, they use derivations to make sure that you understand kind of not only the content of each equation, but you kind of know how you can use it and manipulate it to do what you want. We're solving for VF, and it needs to be in terms of MC, VC, and physical constants. So let's see, begin by writing a fundamental physics principle. We just used in the last one, P initial equals P final. Let's see if that still works. So that's going to be M initial, V initial equals M final, V final. That seems like it's working so far. We have our V final that we're solving for. Let's start plugging some things in. So for the initial momentum, we need to take into account both the cart and the block. So the initial mass of the cart is MC. It's moving at speed VC, plus the initial mass of the block, 1/5 MC. But then, like we said in the last question, it has no horizontal motion because it's just being dropped straight down. So that speed would actually be 0, letting you cancel that out. And that is something that you're able to that some people might be able to just recognize. You don't have to even write that down. It's going to be equal to our M final, V final. M final is going to be at T equals T2. We have both the car and the block. So it's going to be our MC plus 1/5 MC. That MC has an assumed coefficient of 1, so 1/5 plus 1 is going to be, actually, I'll just write it out just in case if anybody's having trouble kind of visualizing that. So we have our mass of the final system. It's going to be our 1 MC plus 1/5 MC. And then times our V final that we're solving for. So it's going to be 6/5. Just going to clean this up a little bit. 6/5 MC V final equals MCVC. And then since we have an MC on both sides, we can actually just cancel that out. We have 6/5. We have VC equals 6/5 VF. To isolate that VF, we got to divide by 5 or by 6/5, which is equal to multiplying by the reciprocal. So 5/6 VC equals VF. And then let's just kind of check this. Did we solve for VF? Yep. Is it in terms of MCVC physical constants? The only variable present in our final equation is VC, so yeah, it is in terms of MC, VC, or physical constants. All right, so there's our final answer for that question. I'm just gonna move it up in case we need it for the next one now. Then I'm gonna go ahead and erase kind of all this. Next question, we have another derive. Like I said, they love this for because it's a good way to show that A, you know the material, and B, you know the math. So we're deriving an expression for the change in the kinetic energy. So that's delta K. So we're not talking about momentum right now. We're actually talking about kinetic energy in the block cart system from t equals 0 t equals t2. So we're talking about from there to there in terms of MC, VC, physical constants. So pretty much the same variables as before. Begin your derivation by writing fundamental physics principle or equation from your reference information. So let's see, they give us delta K. Why don't we let that be our fundamental physical physics principle, delta K, which is, we know delta is going to be final minus initial, so it's K final minus K initial. And then what is K? Well, we know according to our reference sheet, kinetic energy is 1/2 mv squared. So then we have 1/2 m final times v final minus, oh, sorry, I forgot the squared, time, minus 1/2 m initial v initial squared. So let's start plugging stuff in with maybe stuff that we saw for or stuff that they gave us. We have 1/2 m final. That's going to be at t equals 2. That's our block and cart system. So like we said last problem, it's going to be 6/5 times vf squared. We just solved for v final. It's going to be 5/6 times vc squared minus another 1/2. Our m initial is going to be our cart. And then also the block would, you would technically have, like technically you also evaluate the block, but we know that the block's being released from rest. So it's at rest, velocity is going to be 0, has no energy. So we don't really need to include that. So our cart is mass MC, V initial is going to be that speed VC. So now just got it, and then that's all equal to delta K. So now I just got to do some simplifying. Oh, forgot my VC squared. 1/6 times one, or sorry, 1/2 times f 6/5 is 6/10, 3/5. Sorry, just kidding. 3/5 times 5/6 squared, 25 over 36 times VC squared minus 1/2 MCVC squared. And then actually on this previous one, I forgot an MC. So I'll just throw that there. This looks a little complicated to evaluate at first, but really you could just say like that 3 divided by 36 is going to be your 12 on the bottom. 25 divided by 5 is going to be your 5 on the top. And then still have your M del MCVC squared minus that same 1/2 MCVC squared. Combine like terms, the 5/6 and the 1/2 gets you negative, or 5/12 and negative 1/2 gets you negative 1/12. Once you find a common denominator, that MCVC squared is going to stay. MCVC squared. And then that's all equal to delta K once again. All right, so let's see. Does this final answer work? Did we solve for delta K? Yes, we did. Is it only in terms of MC, VC, and physical constants? Our only variables are MC and VC. So, yep, just gonna get rid of this before we go to the next question. Consider the case where a new block is dropped and collides with the top of the cart. The new block slides along the cart during the collision but does not slide off the cart. The time interval from when the new block collides with the cart and moves together with the cart is delta t. During delta t, there is a frictional force between the new block and the cart. Indicate whether the x component of the momentum of the new block cart system increases, decreases, or remains constant during delta t. So, what makes kind of these questions a little hard, especially the justification part, is that, I mean, there's just so many different things. There's so many different ways you could word it, so many different maybe things you could say in some cases, but really just you want to make sure that you're describing kind of the concepts behind it accurately, which it is kind of hard to do with some of these things. So I think we can do the indicate pretty easily. It's gonna fall and it still sticks because it does not slide off the cart. So it's gonna act very similarly to kind of what was going on in this situation. So it's just gonna remain constant because I mean, the block just fell on top of the cart, similar to what happened before. This justify, I'm actually gonna pull up the AP classroom or the AP kind of rubric that they used. So for the first point of your justification, you need to indicate that either the frictional force exerted on the new block by the cart is equal in magnitude and opposite direction to the frictional force exerted on the cart by the new block. Frictional force internal to the new block system, net external force is still zero. Frictional force does not cause net external force. So they just want you to identify basically up front, even though there's frictional force that's happening between the block and the cart, so there is no force actually affecting the motion of the block cart system. And then the second part is you have to indicate one of the following. The change in momentum of the new block system is equal in magnitude and opposite direction to the change of momentum of the cart. The impulse exerted on the cart and the impulse exerted on the new block are equal in magnitude and opposite direction. The correct relationship between the change in momentum of the block cart system and the net external force. So really, here they just want you to say the momentum's not changing, pretty much. So it's a little confusing. And they also want you to include the fact that what changes momentum is that net external force that's not present. So they do a pretty good job of explaining that in their example response. The momentum of the new block cart system will remain constant because the frictional force exerted on the new block by the cart is internal to the system, and only a net external force will cause a change in momentum of the system. It's probably one of the best ways to word it, but I mean, there are just so many different ways you could state your answer. I'm not really gonna write a particular one just because as long as you're saying that this frictional force is not affecting the motion of the block cart system because it's between the block and the cart, so it's internal. And then you also just have to identify that the momentum stays constant and isn't changing because only that external net force is able to change momentum. Otherwise, momentum's going to stay constant. All right, and that is it for this video. Let's stop sharing real quick. All right, I hope you guys enjoyed. I hope that was shed a little bit of light and maybe any questions you might have had, any struggles you might have been having with the FRQs in AP Physics 1. It can definitely be a lot, especially at first, but once you kind of start practicing the FRQs more, it'll become more natural to you. And just especially the derivations, that's what killed me at first, but just kept doing them, got used to them eventually, and was able to obviously do them on the exam. Uh, Next, I'm gonna try to drop videos every Friday, every couple weeks, just going over another FRQ, maybe sometimes doing some sort of review that could also help with MCQs. But like I said, I prefer studying and hammering the whole FRQ section. And I know that this series is made for AP Physics 1. If you guys have any questions, maybe on other AP exams, maybe I could help with them. I have taken 12 exams so far in the process of taking five more AP classes during my senior year. I've been around a lot of these. I will definitely be open to shedding some light on any questions you guys might have. All right. Thank you guys so much for coming or for watching this video today, and I hope you guys have a good rest of your day.